In case I forget to tell you, again, finish the sheet due tomorrow. All right, so you got the pressure question. All right, so let me use magnets because it's just more fun. So 1, 2, 3, and 4. Okay, so we got 4 reactants and we got 5 products. Actually, you know what? Sorry, we're gonna change this. Actually, let's make it 15, so you don't have to erase anything. Just add a 1. Okay. I'm making that dramatic on purpose. All right, so we got 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, all right. Now, I hope this is going to make sense right off the bat. Otherwise, we got to dig ourselves out of a hole here. All right, let's say randomly pick Selim, Reagan, Sean, and Emma are in this side. Who's the rest of you and me and other students and teachers are in this side. Okay, so let's say this is like a metal container that we're standing in. Okay, so try to imagine it. So I don't even remember who I just said, but the 4 of you are here, the 4 of you are here, or the rest of you are here, and then there's more. So there's 15 of us in this one. Four of us here. The reason I'm using you is just so you can be a little more mentally engaged. So these compartments are supposed to be the same size. Okay. This is the reactant compartment. This is the product compartment. Okay. So imagine we're standing in this metal container, like an elevator. All right. Who's more crowded?
That's it.
Products. Do we all agree? Okay. So who's less crowded? Who has more space? So now we're gas particles. Imagine we're gas particles. Okay, so the analogy, you gotta go with me. So what do gas particles do? Move around, bounce around, okay? Who's gonna collide more often? These. It's not even close, right? What's that gonna create? More pressure. Okay. So there's gonna be less pressure here, more pressure here. Now, let's say the box, so actually I'm going real slow to make sure we got it. So there's less space in here, more space in here. They're free to move around, probably less collisions. They would feel more comfortable. Probably feel a little claustrophobic over here. People keep bumping into each other. Okay? We all agree. Now, let's say pressure, not the pressure, sorry, the box, the container, starts to shrink. Top of the ceiling, the floor, and the walls start closing in on us. Which side's gonna probably start to panic first? This side, okay? I don't want to pop like a grape, right? So who has more time to figure out to save them? Like, what are we gonna do, right? We're gonna have a lot more time, right? Because if these, say it with me, if these people huddle together, you actually have a decent amount of space, right? Here, not so much, okay? So this is why it's silly, but this is actually the entire concept. When you increase the pressure on a system at equilibrium, the side with more moles feels that pressure first. Does that make sense? Yeah. Now, some kids think kind of more advanced or deeper about it. They're like, well, how do you have sides of a reaction, right? Because if you have like a flask or a container and the reaction's happening, it's all one container. And you're 100% right. This is just how I teach it. This is how books teach it. This is just to help conceptualize what happens. This isn't actually how it works, right? They wouldn't be separated in like a container, like ammonia with its hydrogen and nitrogen. They'd all be bouncing around together. But let's just assume this is how it looks because it really helps us understand. So if we increase the pressure on this side feels the pressure first. Agreed? Okay. Now, what's one thing the people here could try and do to alleviate some of that pressure? Now let's say so the walls, everything starts closing in, but then it stops. What could the people over here, so we're not going to like kill everybody, okay? So what could people over here maybe try and do to alleviate some of that pressure or create more space? Okay? Remember, this is Le Chatelier's principle. So what does that mean? There's shifting involved. So
Go to
So,
that side.
if the
That's not-
pressure on this is increased, some of these particles are going to try and shift. So let me add this. Let's say this is kind of like one of those semi-permeable membranes. Remember that from biology? Like certain things can go through, certain things can't. Let's say there's a door. Okay? Some of these people can go over there if they want, or some of these people can go over there. What do you think would be preferred? If I'm over here, I'm gonna get the hell out of it. Okay? I'm going over here. Okay? So if I start feeling claustrophobic, or I feel very like under a lot of pressure, people are getting close to me, walls are caving in, and I'm starting to freak out, and there's a door I can get through, I'm gonna take it. So that's exactly what happens, and this is the best way I can teach this. When you look at a reaction at equilibrium, and I use R and P to keep it simple, right? You can have N2 and H2, there's more complicated examples. But if you have 4 moles here and 15 moles here, and you start squeezing this together, increasing pressure, what actually happens is these particles will try and shift over to the reactant side. So if I move some of these over here, and actually then they become reactants. So if I start shifting these, now all of a sudden, this side, yeah, becomes a little bit more crowded, but this side becomes more spread out. That's exactly what happens with pressure changes for this concept. This is what I want you to learn. If you increase pressure, it always shifts to the side with the lower number of moles. I just happen to pick the reactants with the lower numbers. I could flip this. If I had 15 of those and 4 of those, if I increase pressure, it's going to shift to the side with the lower number of moles. And again, the reason for that is because of all these particles are crowded together. They don't want to be any more crowded than they already are. So they try and get out. They try and create space because that's what gases do. They go from high pressure to low. So this side would experience high pressure first, so it would go towards the low pressure, which is where there's less particles. Does it make sense with the analogy, at least, hopefully? Yes, no, maybe? Sell? Does it make sense? Forget the chemistry involved. If you had 15 people squished together and only 4, that naturally we would want to just get to more space to feel more comfortable. That's all I'm asking. If that makes sense to you, then that's good. Guess what? The opposite is true. And that's where the real life analogy breaks down. If you decrease pressure, now we're going towards the higher number of moles. So if we go back to the 15, and this is where it's very hard to kind of teach like a concrete example. So if you go back to the original scenario, if you make these boxes bigger, if you expand the boxes, the container that you're in, so there's more space, what actually happens is the reverse. Now these are going to want to go over here. And the best way I can explain that is when you're at equilibrium, so this picture right here, there's a certain amount of space over here, and there's a certain amount of space over here, and this reaction wants to maintain that space. So if this box gets bigger, and this box gets, so if it grows, there's too much space. So what happens is these particles go towards the higher number of moles to fill in that extra space. It wants to try and get back to where it used to be. It's not easy, I get that. That's the best, easiest, most straightforward way I can explain it. So what I really focus on is the increased pressure. If you can understand increasing, this side becomes very uncomfortable first. It's going to want to shift this way, then that's all I can ask. If you can remember that, you're good. The lower pressure is the opposite. Sometimes I teach things that way. It's not the best, but I think it helps. It gives you a shot, at least, at getting these right. So when you increase pressure, we shift towards the lower number of moles. When you decrease, you shift towards the higher number of moles. We're going to write that down, then we'll do a practice problem, and then that's going to be about it. All right, so if we take this example here, and this is only gases, by the way, right? So gases feel pressure, liquids and solids don't. So if pressure is increased on a reaction at equilibrium, it shifts towards lower number of moles. And again, the analogy is the side with more moles feels that pressure first, and it gets very uncomfortable. It doesn't want the increased collision, so it shifts to the side with lower moles to kind of alleviate some of that pressure, to gain more space. So the analogy again with, you're in an elevator or a box and it's closing in, you can, imagine that doesn't feel good, kind of scary. So if you can get out, there's a door and you can get out, you're gonna take it. That's the best I can do to try and get you to understand the concept here. So this always happens. It doesn't matter where that is. I just happen to pick the products with 15, but if we flipped it, then we'd be shifting to the right. So that's the biggest part of this I want you to remember, and then the opposite is true. So I'll just write, if we decrease pressure, shifts towards the higher number of moles. Higher or larger number of moles. So we'll do a practice problem here, and then maybe a couple, and then if there's any time, there'll be a little time left, you can start your homework. I'm not going to start anything new right now. Alright, so let me give you an actual reaction, ask you a question, and then we'll go from there. Alright, so, Sean, how you doing today? Good. What if the moles are equal, Sean? So I'm talking about greater number on the left, greater number on the right. So what happens if this was 15 and 15? What do you think? What's that? No shift. Very good.
Does that mean that they're at equilibrium
Oh, no. That's equilibrium. So, 3 words for equilibrium. Balanced, constant, equal. So, the only thing that's equal at equilibrium, I'm really glad you said that. You're not alone, trust me. The forward reaction happens at the same speed as the reverse. So the rate is equal. These other 2 words are probably the most important thing to remember. So when this is at equilibrium, 4 and 15 are balanced. That's your seesaw. What does that mean? Their concentrations are constant. So if they happen to be equal, that's just the way it is. They don't have to be equal to be equilibrium. But, like Sean said, if the moles on the reactants and product side are the same, this doesn't apply. This does not apply. There's no shift. So if I increase or decrease pressure on this, nothing happens. Okay, here's a real question for you. Write this down. Let's go with, we'll make some water. 2H2 gas plus O2 gas in equilibrium yields 2H2O gas. Question is, what happens to the concentration of H2 gas if pressure on this reaction is decreased? So that's the hardest way I could ask it, right? That's the hardest Regis question. The easier version would be, what direction does the equilibrium shift if pressure is decreased? This question, you have to figure out which way it shifts, then how does it affect the H2? So I'll give you a minute or so, a couple minutes to figure this out. We'll go over it, and then you can start working on your homework if you want, but we will be done. Come on. There we go. Okay, good. All right. That it's just for entertainment for me. Purely for my entertainment. How many moles of reactants? How many blue ones?
3.
3. How many moles of products?
2.
2. Now I didn't do that right? It should be diatomic, diatomic. That should be 2 different colors. I don't care about that. I have 2 H2. Should be diatomic. 1 O2. So 3 moles and 2 moles. So which way are we shifting?
That way.
So if we're decreasing pressure, which way do we shift? Towards the higher moles or lower moles?
Or the higher.
Higher. So which way are we shifting? Left. If we're shifting left, are we making, and this is Kara's turn, are we making more H2 or are we using it up if we're shifting left? So, don't overthink this. If we are taking this and moving it over here, it can't be water anymore. It turns into O2 and H2. So if we're shifting this way, are we making more of this or using it up? Making more. So the answer to this question is concentration increases. We shift left because there's more moles here, that's the rule. And if we're shifting left, we're making more of both of these. So the answer is concentration of H2 increases. I know it's not that easy. Your homework's going to practice. I'm going to give you more practice tomorrow. Well, it's going to be homework. I know, don't hate me too much, but you'll have more practice problems. So that's it. You have a few minutes. You want to start your homework? Go ahead. If not, just, I guess.